Hello, my name is Marshall Folkman. Today I'm going to present to you my experience with creating an AI model related to predicting the excitation current in a synchronous AC motor. I knew I wanted to do some sort of a motor control. The model AI. This is a machine learning model, supervised machine learning model. In this presentation, I'll walk you through what led me to the particular data set that I chose as an example for this learning experience, and the motivation behind that a little bit, without being too long-winded, and then explain my process of analyzing that data, cleaning the data, and then building a model on that data, building several models on that data, and exploring and comparing the performance of those models for this particular data set, and what can be done with this model for future data sets and similar motor application scenarios. This is a very popular, as an embedded systems engineer that's dabbling in the AI realm, this is a very, very applicable problem in my world. So that's why I chose this. So I'll start here just kind of by pointing you. So in my problem description here, I have cited this source of where I pulled this data set. I did not sample this data myself. This came from the Kaggle website, and this is a fairly new data set. It's not huge. NASA and some others have some larger ones, but they're very, very complex and take gigabytes of data. So the motivation behind picking a motor, it might seem weird to some that aren't familiar with motors, but this is actually really big money in the industrial industry, and even starting to get into other things like agriculture and stuff like that. But monitoring a lot of behavior of motors, like vibration and currents and things like that, over very long periods of time, can give you insights on when that motor is likely to fail. And that may not seem like a big deal. Okay, it's a pump or it's a motor, it's doing something. Just when it breaks, just fix it. It may only take a couple hours or whatever. Well, for anyone who's ever worked in a manufacturing plant, the way lean manufacturing works, a certain process goes down for even a few hours. It can be hundreds of thousands of dollars in loss for that company. It can cause a lot of headaches for people in that plant, all throughout the plant. So it's a very, very big deal to be able to predict when things are going to fail, and there can even be safety concerns along with that too. So it's a very, very, very big deal to be able to have the ability to predict when a motor will fail. This particular data set doesn't do that specifically, but it's all kind of in the same line of thinking, where you're really monitoring the load current on it, and power factors and things like that, along with vibration. This particular data set does not do vibration, but due to the massive amount of hours that a motor can that a motor needs to be sampled, all the massive amount of data that needs to be sampled, to be able to really pick up on the behavior of what that motor does, all the way up into the point of failure. Very, very time consuming, and that's why there's other data sets like the one here from NASA that does a fairly good job, but is a tremendous amount of effort to really sift through that. And for this particular assignment, it really wasn't. It requires a little bit more than I think this assignment calls for. So that's why I chose this one. It just monitors some of the more important features in the set. So back to my Juniper notebook here. So that's why this was chosen. Hopefully that's the most long-winded part of this. I'll try to make the rest quick for you. But yeah, so in analyzing this, I'll admit I actually cut out, there was one feature here in this data set I actually didn't even include in my report because it actually is the exact same information as what we were predicting. So what we're doing here is we're trying to predict the excitation current of the synchronous machine. In other words, the current that we're going to give the motor in order to manipulate the speed at which it runs at, the rotor runs at. And the thing I cut out here was the changing of excitation current, which you know, if you just do a quick subtraction, it actually is the same thing. So even though I'm not showing it in my report, what I found was once so you're predicting this number 5 here feature, and then the rest of these 4 were supposed to be features. But once I actually got into it, I realized there was a direct 100% correlation between these two because they're the same thing. So I obviously wasn't even worth entertaining that. I'm not sure really why the poster of this data put that in here. So I didn't even want to have to present that too much here. So that got eliminated. So if you're wondering why my features don't match the cited source, that's why. I just deleted it before I even started, right out of the data set. So knowing that, it's still needed cleaned a little bit more. So you'll notice here that we have a feature that's called power factor, but we also have a power factor error. And I also noticed as we go down here, you notice these 2 graphs on the right here in the scatter plot. You have a power factor here, and you have a power factor error. Well, I was already kind of picking up on this just from the graph here. Very, very similar data sets, right? Not the same, but very, very similar. And but I wasn't convinced that I needed to eliminate one of them, but I could kind of see it was going that way once I plotted that. And then I went ahead and did a correlation matrix on that, and from that you can see the power factor and the error power factor. They're pretty much, you know, they're different data sets, you know, when you actually graph them, but they're just mirror images of each other, you know. So my suspicion was proved correct as I saw the correlation matrix where the power factor, so the error of power factor has what you'd expect, like a positive you know, number here between 0 and 1, which was 0.86. You can see it right here. The power factor was just the inverse of that. So again, it's the power factor and the error of the power factor. The data supports what your intuition might think. So similar kind of a thing. I don't know why the person who was putting this data set together threw that in there. Maybe just for the experience of having to clean your data rather than just look at it and not understand what it is the data actually is and why it's in there. But yeah, so clearly it was understood that, yeah, I need to get rid of one of these, and so I chose to get rid of the power factor because it was negative, and I thought, hey, let's just keep everything positive. If we eliminate that one, then we only have to deal with positive correlation coefficients, and I thought that would be a lot simpler. So that's why I did that. So what I thought would start as 4 features turned into just 2. And the data, I'll be honest, kind of scared me at the beginning. And I was worried that I would be able to get a real accurate model. I knew I'd be able to put something together, but especially this load current. Okay, so now the features we're going to be looking at is load current and the power factor error is what we're going to be just with 2 features, trying to see how accurate and very, very erratic, eclectic data sets here, and we're going to see if we can put an accurate model together with only 2 features of eclectic data sets. My expectations were not really high. So yeah, so after looking at that, so now we move on to the actual analysis, where we're actually going to start putting models together and training and testing the data, using the training data. So for splitting the data, I did kind of what seems to be the standard norm, where I'm taking 80% as my training data, and then just reserving the last 20% to test. And I do that consistently throughout, so I'm trying to be as fair as possible to these models. So I did 3 different models. The first one is a simple linear regression model that utilizes the load current feature. Okay. I knew this one would be the worst, so I figured I might as well start with that so we could kind of compare models and see how we're improving each model I went to. We're taught that you should always pick the simplest model possible that you actually need, because in practice, AI takes a tremendous amount of computation, especially for something like this, for what I do, which is on embedded systems. So computation and computer resources becomes a very big deal to me. So for me especially, it's a big deal to pick as simple of a model as possible. So I started with linear regression, tried to see what I could do there, seeing if that would work. Picked the feature that seemed like it would be least likely to work, and that was very true. The R squared gave me a 0.17, about a 17% R squared value or whatever. Very poor. That's you at least want to get above 50%. So basically, this is very, very poor. You would not want to predict anything off of just this one feature, especially with just using linear regression. So this was a good starting point. Just looking at comparing that to the load current alone, and that was definitely not a good metric. At least for linear regression, it wasn't. There are some patterns in here. There's maybe some KNN might have done well, but I didn't even get that far. So we'll get to that in a minute. So then I tried the exact same approach, simple linear regression, but this time doing the other feature, which is power factor error feature. And looking at that, that gave me a significantly better R squared, but still pretty poor. I mean, you could maybe implement that in practice, but I wouldn't. That's pretty poor. You really want something probably in the 90s at least, it seems like. So much better, but still poor. So we knew we had to keep going. Then that brings us to the random forest model. I did not think this would be my ending model to look at, actually. The reason I picked random forest is because from what we were taught, random forest is where it shines is where you have a lot of features, which is true. And so because we only have two features, I thought that, well, random forest is really good, but it's very prone to overfitting, and it shines really well with having lots of features, not too many features, because that's where it starts to overfit. But I thought this would be a little bit too complex for what I was needing. So I basically picked it because I kind of wanted to try to find an example of something that would overfit. And to my great surprise, and I don't think I did that many estimators really. I mean, that's kind of a lot. I didn't play around with the estimator values too much, but yeah, that's to me that's not a ton of estimators, and without even needing to play around with that. To my great surprise, it performed amazing, almost 99% R squared value. Just blew the linear regression models right out of the water. So that was very, very impressive to me that did that. Also, I had an MSE and an RMSE values that were very, very low too, which indicates that we have indicating better predictive accuracy. So that was very, very enlightening as well. I didn't display that for the other ones to compare that. Really, if you want to compare apples to apples, what we really have, because of the nature of the linear regression, this is kind of our metric for this. But and I know there's other metrics, but this is the metric that is allowing us to compare apples to apples and the models and comparing them side by side. So this definitely seemed to be the winning guy, and that's basically my conclusion. Where yeah, I think if I was in the real world doing this, and I was trying to predict the excitation current on this motor to save power or whatever, even if you weren't trying to predict failure long term, if you did that, you'd probably want to also include vibration data, but at least. But in this particular case, all we needed was to monitor the excitation current, and knowing that could help save power, and so yeah, if this was in real practice, I would use this in the real world. So anyways, I'm out of time. Thank you for watching.